All right, guys, here's the last lesson in our probability distributions unit. These are hypergeometric probabilities. So, first of all, let's recall what we know about probability. Take a look at this example here. We've got 5 dogs and 6 cats at the local SPCA. Right? They want to choose 3 of their animals for a special advertisement for the adoption of animals. So what we want to know is, what is the probability that exactly 2 dogs are chosen for the advertisement? So think about this for a moment, pause the video, determine how you would solve this problem, and then continue. All right, so hopefully you remembered how to do this. We are using combinations. If there's 5 dogs and 6 cats in total, and I want to select 3 of them, the different probabilities that I could have, the different options that I have, is having 0 dogs with 3 cats. That's one outcome. 1 dog and 2 cats is another outcome. 2 dogs and 1 cat, or 3 dogs and no cats, because I'm selecting a total of 3 animals. All right, so those are all my different outcomes. Now, the number of ways I can do this, if we go back to our combinations unit, I have 5 dogs in total. I have to choose 0 of them for my first outcome. And out of the 6 cats, I have to choose 3. So 5 choose 0 times 6 choose 3 is the number of ways I can choose 0 dogs and 3 cats. All right, continuing that same pattern for each of the different outcomes. And I also know that my total number of possibilities, if I have 11 animals, 5 dogs and 6 cats is 11 animals, and I want to choose any 3 of them, those are the total ways I could choose any 3 animals. Okay, so if I add up all these outcomes, all these number of ways, I should get the same as this 11 choose 3. All right. So in order to find the probability of exactly 2 dogs, I'm going to be looking at this row here, all right? And what I want to do is I want to take this number of ways of choosing 2 dogs and 1 cat and divide that by my total. So I have 5 choose 2 times 6 choose 1 divided by 11 choose 3. And this is going to give me the probability of exactly 2 dogs. All right, so you're going to need to remember this, because this is what our formula is going to be based on today. All right. The other thing I want you to think about before we continue is I want you to think about card games. What do you recall about the probabilities of card hands? Hopefully, what you're thinking about is that they are dependent. Every time I deal a card out of the deck, it changes the probabilities of all the other cards that are still in the deck, because there are less cards in the deck and there are less cards of the suit I just dealt, the value that I just dealt. Okay, so my probabilities change every single time I deal a card, and that is dependent events. So remember, in our binomial distribution, we were dealing with independent events where the probabilities were the same every single time. Now, as you can guess, we're dealing with dependent events where the probabilities change every single time. Okay, so this is known as hypergeometric probability distributions. Probabilities in these trials are dependent, as we just discussed. Every selection reduces the number of items available for the next trial. That's what dependent means, which means the probability of success changes as every trial is made. So again, there are only 2 outcomes. We either have success, something happens, or failure, it doesn't happen. So in this way, it is similar to the binomial distribution. We are looking at success or failure. And the random variable is the number of successful trials in an experiment. So that is also the same as the binomial probability distribution. So really the only difference is this is dependent, where binomial distributions were independent. Okay? Now, our formula looks very different, though. So our formula for hypergeometric probability distributions looks like that dogs and cats formula that we just looked at. All right, so I have 3 combinations here. The first combination is the thing I am looking for. This is the number of ways of getting that success. So A, choose X. A is the possible number of successful outcomes. Remember in my dogs example, I had 5 dogs. I've got 5 possible successes on a dog, 5 different ways of the dogs there, okay? X is the number of successes we want. So I wanted 2 dogs, so X would be 2, all right? So this is your dogs. These are a success in this case, all right? Now, not that cats are bad, but cats in this case is considered not a success, all right? It's the other animals because we were just counting the number of dogs. So in order to figure out how many of those failures or those not a dog things that we have to take my total number of animals, total number of outcomes, and you're going to subtract the number of successful outcomes. So this figures out that there's 6 cats because I had 11 animals and 5 dogs. So 11 minus 5 is 6. That's my 6 cats. The total possible outcomes is N, right? The A is the possible successful outcomes. Okay. Now we are choosing R minus X. Well, R is the total number of trials in the experiment. This is the 3 animals that we are choosing for this adoption promotion. And X, remember, is the number of successes we wanted. That's my 2 dogs. So 3 minus 2 is 1. So we got 1 cat that we also needed. All right. And then in the denominator, we have N, choose R. My total 11 animals, choose any 3 animals. All right. So this looks exactly the same as you would expect it to look. Sometimes you're not even going to memorize or use the formula. You're just going to think it through like we did in the dogs and cats question, and you know what your values are from there. Okay. So your expected value formula, E of X, the expected number of dogs, is equal to R times A. So again, R was the number of trials, so it was 3 animals. A was the possible successful outcome, so this is my total number of dogs. So 3 times 5 is 15. And we are dividing by N, which is the total number of possible outcomes, the total number of animals in this case, which was 11. All right, so you're going to plug those numbers in and you will get the expected number of dogs in the picture. So here's another example, jury duty. So we're going to calculate the probability distribution for the number of women on a civil court jury. Civil court jury consists of 6 people. We're going to select from a pool of 8 men and 10 women. All right, so we're going to do a probability distribution, and then we're also going to calculate the expected number of women on the jury. So first of all, our probability distribution. We have a 6-person jury. I'm choosing from 8 men and 10 women. So A is 10. It is the 10 women, the possible successful outcomes. X is the number of women on the jury. This is the number of successes we want because this is a full probability distribution. X is going to vary from 0 all the way up to the full number of people on the jury. So 0 to 6 in this case. N is 18. So it's my total number of people, my total possible outcomes. And R is the number of trials I'm doing. So in this case, I'm selecting 6 people. It's a 6-person jury, so R is 6. All right, here we go, plugging all those numbers into my formula. Again, A was 10, the number of 10 women. N was 18 people in total. R is 6 people on the jury. And X is the number of women on the jury. I can vary it from 0 women on the jury all the way up to all of the women, 6 women on the jury. All right. So calculating the full probability distribution, you can see my probabilities off on the right-hand side here. Now, these are crazy big decimals. I should have reduced these down to about 3 decimals would have been useful here. All right. So when you're doing your questions, you can reduce these, round these to 3 decimals. All right. And we can see the probability distribution, the probability histogram here. And finally, my expected value, I plug in my values, R times A divided by N, and I get 3.3, approximately 3 women on the jury. All right, that's it. That's our hypergeometric probability distributions. and we'll see you in class.